Wanted to do a little bit of an introduction into the next section, only to try to get some definitions down so that we can spend a little bit more time on actually doing some example problems rather than going through definitions and then plus example problems plus talking a little bit about concepts. I think it's just a little bit easier to go through the definitions in a video so that you have them before we start talking about them in class. So all right, let's say we have a matrix. So I've identified this matrix by its entries. Notice that we have an M by N matrix. So we have M rows, N columns. The row vectors of A are just the vectors that we make from the rows of A. So R1 here would be A11, A12 out to A1N. R2 would be A21, A22, out to A2N, and so on up the line until we get to R sub M. Similarly, we can define the column vectors. So those are just the columns of A. So column vector 1 is just the column of the A11, A21, and down to AM1. Column vector 2 is the second column. So on down to column vector N is the nth column. Now notice that when we look at our row vectors, we have n components, so we can think of those as vectors in Rn. The column vectors, however, have m components, since we're going down the rows, so those can be thought of as vectors in Rm. So our row vectors are in Rn, the column vectors are in Rm. So I could have actually written these horizontally like the other ones. The way we write it, horizontally, vertically, however, doesn't really matter. I can think of these as just being components of a vector in Rm. All right. So there's some spaces that we can define associated with a matrix. And in particular, there's three big ones that we're going to talk about. The first one is the row space. So the row space, which we denote with row of A, that's the span of the row vectors of A. So remember, by span we mean set of all linear combinations. So if I write that in set notation, the row of A is just every linear combination you can make using the rows of A. Now notice that this is going to be a subspace. Remember, the span of any set of vectors is always a subspace. So the row space is always going to be a subspace of Rn. Remember, we can think of the row vectors as being vectors in Rn, so this will always be a subspace of Rn. The column space of A, we denote this was call of A, if you will. That's the span of the column vectors of A. So again, that just means set of linear combinations of the vectors in A. The column vectors. Notice again that these were vectors in Rm, so the column space is going to be a subspace of Rm. All right, another definition that we have here is the definition of rank. So the rank of A is going to be defined as the number of pivots when we do the reduced row echelon form of A. So notice that we could always count number of pivots in the rows, or we could count the number of pivots in the columns. That's going to be the same, right? Because we can't have two pivots in one row. We can't have two pivots in one column. So when we count number of pivots, we can either go by rows or by columns. That'll be important for us later on. Next definition that we have with a space associated with a matrix is the third space that we're going to talk about in this particular section, and that's the null space of a matrix, denoted with null of A. And this is something that we've already studied. We've talked about the null space, we just haven't called it that before. The null space is just the set of solutions to the associated homogeneous system. So if you think of A as the matrix of coefficients for a homogeneous system, then the null space is just the set of solutions to that system. And then finally, the nullity of A, which we define oh so cleverly as nullity of A, is the number of pivotless columns in the reduced row echelon form of a matrix. And again, this idea of number of pivots in the reduced row echelon form and number of pivotless columns in the reduced row echelon form are things that we're going to talk about in class, why we care about those particular numbers. Like I said, right now I just want to get some definitions down. So let's look at a specific example, and then we'll leave the rest of the concepts for class. Here's a matrix A, We've got a 4 by 5. We can list out the row vectors of A. Those, again, are just the rows of A, so easy listing of those out. Notice that those vectors, in fact, are vectors in R5. The column vectors, again, just a simple listing of the columns of A, and those are all vectors in R4. Okay. So one thing I do want to mention from this, just as a lead into stuff that we're going to talk into class, notice that we have 4 vectors in R5. It means that this is not going to possibly span R5. Remember, to be a spanning set for R5, we're going to have at least 5 vectors in R5. They could be linearly independent. I don't know. Not by looking at them. I certainly don't know if they're linearly independent. But I do know that they cannot possibly span R5. Likewise, with these column vectors that we have, these are all vectors in R4. I know that these 5 vectors cannot be linearly independent because when we have a set of vectors in R4, the most vectors you can have in a set to be linearly independent is 4. So I know that the rows cannot span R5. I know that the columns cannot be linearly independent in R4. Now, again, it could span. I don't know. Not yet. But I do know that it's not linearly independent. And actually, we see that here when we do the reduced row echelon form of A. When I see the reduced row echelon form of A, I've got pivotless columns. That tells me right away that we have free variables. We don't have we have an infinite number of solutions to the homogeneous system, meaning again that they couldn't possibly be linearly independent. I also notice that these don't span because I don't get a pivot in every row. So these didn't span either, all of R4. All right, so looking at the reduced row echelon form, the rank is 2 because we have 2 pivots. The nullity is 3 because we have 3 free variables. It's just a simple counting problem. Literally, that's all we have to do for rank and nullity. Now, one thing I do want to notice is that when you take the rank and add it to the nullity, we get number of columns. And that's always true because think about it, either a column has a pivot in it or it doesn't. So when I take the rank and add it to the nullity, I have to get the number of columns that are in the matrix no matter what, because either a column has a pivot or it doesn't have a pivot. Finally, last little example here is writing the solutions to AX equals 0, or basically looking at the null space of A. The solutions of AX equals 0 can be written as, well, I've got free variables R, or X3, X4, X5, so I can do R, S, and T. So I see the R, the S, the T in component 3, 4, 5. And then solving for each of the X1. When I solve for X1, I get negative R minus 2S minus T. And when I solve for X2, I get negative R minus S minus 2T. So this would be the set of solutions to this system. So this would be the null space of A. And in fact, since these are linearly independent, these 3 vectors would actually form a basis for the null space of A. So like I said, we're going to talk more about these in class and do some more of the concepts and do some more examples. I just wanted to get the definitions down so that you were familiar with these before we get into class, because I didn't want to spend 10 minutes in class talking about these definitions when you could watch a video and have them down before class time. So we'll talk about this later.